তৈরি আছে। Hello dear students, and this is Professor Anindya Das from Achievers, and welcome to my lecture series on the second law of thermodynamics. So in the previous two lectures we have discussed about the concept of engine and refrigerator, and we have also analyzed the corresponding statements, the Kelvin Planck and the Clauscius statements. The Kelvin Planck statements basically depicts the working principle of the engine, whereas the Clauscius statement depicts the working principle of the refrigerator. Now we are already acquainted with these facts, and also we are acquainted with two fundamental parameters. One we have defined in context to the engine, that is the efficiency, and another one we have defined in context to the refrigerator, that is coefficient of performance. And we are already acquainted with these parameters. Now, in this lecture, we'll be discussing the equivalence of Kelvin Planck and Clauscius statements. And where is the equivalence originating from? In the previous lecture, I have told that there is a close resemblance between the engine and the refrigerator in terms of a common equation that is satisfied by both these two thermodynamic entities, and that is nothing but mod W cyclic equal to mod QH minus mod QC. So this similarity depicts that there must be an equivalence between these two thermodynamic devices, that is the engine and the refrigerator, and thereby there must be an equivalence between the Kelvin Planck and the Clauscius statements. So in this lecture, we'll be discussing about the equivalence between the Kelvin Planck and Clauscius statements. So in this lecture, we'll be discussing the equivalence of Kp and C statements. In order to interpret this equivalence, we need to have a very sharp analysis of these two statements in a combined manner. And for that purpose, we need to do a coupling between E and R. So at first we need to understand the E plus R couple. You have to couple an engine with a refrigerator. You have to couple an engine with a refrigerator. Okay. So let's see how the free diagram will look like. So you have got a hot reservoir defined at a temperature TH and a cold reservoir defined at a temperature TC. This much is known to all of us. And at first, let us draw a refrigerator like this. And the refrigerator withdraws QC amount of heat from the cold reservoir. Let us write R as the suffix to understand that it's a refrigerator. And it transfers QH amount of heat to the hot reservoir. In order to demarcate it as a refrigerator, I am giving a suffix R. And for that purpose, it requires W cyclic amount of work. Now this W cyclic will be supplied by the engine, because the engine withdraws QHE, the suffix E is given to demarcate it as the engine. QHE amount of heat from the hot reservoir, and it transfers QCE amount of heat to the cold reservoir, and it performs W cyclic amount of work. In case of W cyclic, I am not putting any suffix E or R. Why? Because the work done by the engine is being utilized by the refrigerator. In that way, they are being coupled. The work done by the engine E is being utilized by the refrigerator R, and in that way they are connected. So this W cyclic is same for both the engine and the refrigerator. So basically, W cyclic for the engine is equal to the W cyclic for the refrigerator, and it is simply written as W cyclic. So we lift the suffix because they are same. So in this way they are coupled. So this is the process of coupling an engine with a refrigerator. The engine is performing some amount of work, and that work is being utilized by the refrigerator. In this way, we are connecting the engine with the refrigerator, and thereby we are creating this E plus R couple. So what is the condition? What is the condition for E plus R couple? The condition is mod W cyclic for R should be equal to mod W cyclic for E. If the two entities are same, then their magnitude must be same. The magnitude must be same. So we are writing it in this manner. Magnitude of cyclic work done by the refrigerator is exactly equal to the magnitude of the cyclic work applied on the engine. I'm sorry. The magnitude of the cyclic work done by the engine is exactly equal to the magnitude of the cyclic work done on the refrigerator, and that is W cyclic. Okay. So writing it in this way, and in terms of mod, we'll write it in this manner. Okay. So this is the mode of representation of E plus R couple. And for that purpose, what do we have? See, what is mod W cyclic of the refrigerator? It's mod of QHR minus mod of QCR by definition. We know that. This is equal to mod of QHE minus mod of QCE. Okay. So, mod of QHR minus mod of QHE is equal to mod of QCR minus mod of QCE. So you can write it in this manner. And one important thing has to be noted. This equation is not perfectly okay. Why? Because if you are considering the reference to be engine, then W cyclic is negative. And if you are considering the reference to be refrigerator, W cyclic is positive. So how come they be equal? They can only be equal in terms of their magnitude. That's why we write the equation in this manner. Okay. So you just can't make these two things equal. Because although they are same in magnitude, they are opposite in sign. That's why you write it in this manner. You write it in this manner. Okay. So this is how we couple an engine with a refrigerator. So I think you have understood the coupling of an engine with a refrigerator. The engine performs some amount of work, and that work is being utilized by the refrigerator. Okay. So in this way, they are getting coupled together, and the condition of coupling is that the cyclic work of the refrigerator is equal to the cyclic work of the engine in terms of their magnitude. And this leads to such important mathematical conclusions. Okay. Now, we would gradually move into the logic of this equivalence. For that purpose, let us draw this free diagram once again. Let us draw this free diagram once again. So what we have got? We have got a system like this, where you have got an engine and you have got a refrigerator. They are connected by same magnitude of cyclic work. Okay. And what else do you have? You have QCR, you have QHR, you have QCE, and you have QHE, like this. Okay. So I brought forward the diagram from the previous page. Now, in this diagram, we see that E is abiding the Kelvin Planck statement, and R is abided by the Clauscius statements. So this is known to all of us. This is known to all of us. Now what if we hypothetically consider this QCE to be 0? What if we hypothetically consider this QCE to be 0? If we apply the hypothetical condition that QCE is 0, that means the engine is withdrawing heat from the hot reservoir. That is okay. This is non-zero. QHE is non-zero. So it is withdrawing heat from the hot reservoir. But it is not rejecting any heat to the cold reservoir. It is withdrawing heat from the hot reservoir, but it is not rejecting any heat to the cold reservoir. Rather, the entire amount of heat withdrawn from the hot reservoir is being converted into work. If we apply this hypothetical condition, then we find that the heat withdrawn by the engine from the hot reservoir is entirely getting converted into work. So thereby, what is happening? E is violating the Kelvin Planck statement. E is violating the Kelvin Planck statement. E is violating the Kelvin Planck statement. We find that E is violating the Kelvin Planck statement. Because according to the Kelvin Planck statement, if any heat is withdrawn from the hot reservoir, then it cannot be entirely converted into work. A part of that is to be rejected to the cold reservoir. But here we are applying the hypothetical condition that the rejection of heat to the cold reservoir is 0. That means this E, this engine E is violating the Kelvin Planck statement. But if you ponder into the refrigerator, what do you see? If you ponder into the refrigerator, then you see it is withdrawing QCR amount of heat from the cold reservoir, and it is being supported by some external agency Thereby W cyclic amount of work is being done on the refrigerator, and it is transferring QHR amount of heat to the hot reservoir. So it is completely abiding the Clauscius statement. So in this couple, you see, in this couple, E plus R, E is violating the Kelvin Planck statement, but R is following the C statement. So we find that the given couple comprises two thermodynamic entities, E and R. E is being applied by an hypothetical situation. On E, we are applying a hypothetical situation. So, as we are applying a hypothetical situation on E, that is QC corresponding to E is 0. That means that E is violating Kp, but C is being followed by R. So the couple comprises two thermodynamic entities, E and R, where E is violating Kp and R is following C. E is violating Kp, R is following C. E is violating Kp, R is following C. So what do we expect? What do we expect? What is our expectation? What is our expectation? If the couple comprises E and R, E is violating Kp and R is following C, then our expectation is also like E plus R is going to violate Kp, but it is going to follow C. E is made up of, the couple is made up of E and R. Out of these two thermodynamic entities, E is violating Kp, but R is following C. So what do we expect about the couple? We expect that for the couple, Kp will be violated, but C will be followed. Kp will be violated, but C will be followed. This is being expected for the couple. Now let's check. Let's check C for E plus R. Let's check whether C is being followed by E plus R or not. Let's check whether C is being followed by E plus R or not. We expect that E plus R should follow C. We expect that E plus R should follow C. Now let us check whether it is true or not, whether E plus R is actually following C or not. That has to be analyzed. For that purpose, at first, let us find out the net amount of heat, withdrawn from the cold reservoir. The net amount of heat withdrawn from CR. What is the net amount of heat withdrawn from CR? What is the net amount of heat withdrawn from CR? What is the net amount of heat withdrawn from CR? Naturally, it's mod of QCR minus mod of QCE. Mod of QCR is being withdrawn and QCE is being transferred. This is being withdrawn from the cold reservoir and this is being transferred to the cold reservoir. So the net withdrawal from the cold reservoir is mod of QCR minus mod of QCE. As simple as that. But in this case, we know that this particular parameter mod of QCE, this is 0. We have applied this hypothetical condition. So if we do so, then this amounts to mod of QCR. So this is the net heat. This is the net heat withdrawn from the cold reservoir. Next, net work done on E plus R. Net work done on E plus R. What is the net work done on E plus R? If you ponder into this diagram, you see E is working on R, E is working on R, E is working on R. But there is no external work on E plus R. There is no external work on E plus R. E is internally working on R. E is internally working on R. E is internally working on R, but there is no external work that is being done on E plus R. There is no external work that is being done on E plus R. So, net work done on E plus R amounts to 0. Now, next, the net heat transferred to the HR. What is the net heat transferred to the HR? What is the net heat transferred to the HR? See, QHR is being transferred, QHE is being withdrawn. QHR is being transferred, QHE is being withdrawn. So what is the net amount transferred? QHR minus QHE. Just you have to put the mod. So mod of QHR minus mod of QHE. That's it. That's it. Okay. So far so good. Now, let's turn the previous page. See, we have already got this equation. QHR minus QHE is equal to QCR minus QCE. QHR minus QHE equal to QCR minus QCE. We have already got this. So we have already got this equation. In the last page, we have already got mod of QHR minus mod of QHE equal to mod of QCR minus mod of QCE. We have already got this. So mod of QHR minus mod of QHE, mod of QHR minus mod of QHE can be replaced by mod of QCR minus mod of QCE. We can always write it like this. We have already established the condition for the couple. And again we know that mod of QCE is 0. Mod of QC is 0. This is known to be 0. If this is 0, then this amounts to mod of QCR. Then this amounts to mod of QCR. So what is your observation? You see, E plus R is withdrawing QCR amount of heat from the cold reservoir. It is withdrawing QCR amount of heat from the cold reservoir. It is not being supported by any external agency because no work is done on E plus R. No work is done on E plus R externally. So it is not supported by any external agency. But it is withdrawing QCR amount of heat from the cold reservoir and it is transferring QCR amount of heat to the hot reservoir. So E plus R is such a thermodynamic entity which withdraws QCR amount of heat, from the cold reservoir and it transfers again QCR amount of heat. It again transfers QCR amount of heat to the hot reservoir. So same amount of heat is being withdrawn from the cold reservoir, and that same amount of heat is being transferred to the hot reservoir. And there is no support from the external agency. So these statements show that E plus R will violate C. E plus R will violate C. This is a direct violation of the Clauscius statement. Because according to the Clauscius statement, we know that the amount of heat withdrawn from the cold reservoir cannot be directly transferred to the hot reservoir. That means the amount of heat withdrawn from the cold reservoir cannot be equal to the amount of heat transferred to the hot reservoir, because the thermodynamic entity, that is the refrigerator, has to be supported by some external agency. But here we see that the amount of heat being withdrawn from the cold reservoir is exactly transferred to the hot reservoir in the same quantity, and there is no support from the external agency. So you can say that E plus R is deliberately violating C. So E plus R, so you can say E plus R is violating C. E plus R is violating C. But our expectation was E plus R should follow C. So there is a contradiction. Our expectation was that E plus R should follow C. But we find that E plus R is deliberately violating C. Our expectation was that E plus R should follow C. But we find that E plus R is violating C. So what is the reason behind this fallacy? What is the reason behind this fallacy? What is the reason behind this fallacy? The reason is that as one member of the couple, that is E, is violating Kp, and that is being connected to the other member of the couple R, which is following C, you'll see that the entire couple will violate both Kp and C. So if Kp is violated, then C is also violated. If Kp is violated, then C is also violated. Apparently it was like Kp is being violated, but one member is following C, so the couple should violate Kp but follow C. But we are getting a contradictory result. We find that E plus R not only violates Kp, but it also violates C. Although it was apparent that E plus R should follow C, but under actual mathematical treatment, we find that E plus R is violating C. So what is the reason behind that? The reason is, if Kp is getting violated, then C cannot be followed. So if Kp is violated, C is also violated. If Kp is violated, C is also violated. So in that way, the two statements are equivalent. So we have a very interesting conclusion. Let us write down the conclusion. So the conclusion is, although it was apparently evident that E plus R should follow C and violate Kp, yet we find that under the given constraints, both Kp and C are simultaneously violated by E plus R. This implies that if Kp is violated, then C is also violated. Therefore, Kp is equivalent to C. So you have a very interesting conclusion. You see, although it was apparently evident that E plus R is comprised of two components, E and R. E is violating Kp, but R is following C. So it is apparent that E plus R should violate Kp but follow C. That is apparent. But contradictorily, we find that E plus R is simultaneously violating both Kp and C. E plus R is simultaneously violating both Kp and C. Okay. So what does that imply? That logically implies that if Kp is violated, then C is got to be violated. If Kp is violated, then C is got to be violated. If Kp is violated, then C is got to be violated. And thereby, the two statements must be equivalent. So in this way, we can show the equivalence between Kp and C. So that's all, students, for today's lecture. Thank you all. Bye-bye.